guys, welcome back to my system design series. This is lecture number 32. If you haven't watched the previous video, then kindly make sure you watch it so that you will understand these concepts in better way. So in this video, we are going to discuss some of the topics of chapter number 6 of DDIA book. So today we are going to explore rebalancing partitions in distributed database. Why simple hashing, that is mode and fails, which we have discussed in the previous session. So watch that video. You will find the link in the description. Another is fixed partition rebalancing, dynamic rebalancing, partitioning proportional to nodes, automatic versus manual rebalancing. Okay, so let's start. In distributed databases, data is split into multiple partitions, which is also called shards, so that each server can store the part of the data. This lets the system scale. Each machine handles only its share of the workload. Just think of splitting the large task among the multiple people. Over time, the situation changes. For example, users' request may grow. That makes the dataset gets much larger. Or a server might fail. If the database suddenly has the more queries than before, you might add CPUs. If the database grows in size, you add more disk and RAM. If a machine goes down, other machines must take over its work. All these events means the data and the request must move between these nodes so that no one machine is overloaded. The process of moving the data from one node to another node to restore the balance is called rebalancing. During rebalancing, the database must stay online and keep serving the request continuously. Ideally, it moves only as much data as needed, so the work finishes quickly and doesn't flood the network or disk. After rebalancing finishes, the data and query load should be fairly spread across all the nodes so that each machine have roughly same amount of work. For example, one server has twice the data or request compared to the other server. We want to move some of its partition so that all the servers share the load evenly. Okay, so let's move forward. In the previous lecture, we have discussed that hashing mode and fails. Now let's talk about why it fails. Usually, the naive way of dividing the data is using the hashing the key and doing the modulo by n, that is a servers. This means each key is assigned to one of the n servers based on the hash. At first, this spreads the things evenly. But the big problem is what happens if the number of servers or n changes. That is, one server might be added or one server might be removed. So that makes the n changed, which will let every keys to map to different servers. For example, if the keys hash is 1, 2, 3, 4, 5, 6 and suppose there are 10 servers. So what we will do, 1, 2, 3, 4, 5, 6 modulo 10. So what we will get as 6 as an answer. But what if you grow to 11 servers? Then what you will do is 1, 2, 3, 4, 5, 6 modulo 11, which will give you 3 as an answer. And now what if you will add one more node? So 1, 2, 3, 4, 5, 6 modulo 12, which will go to the 0th server. So as you can see, in each step, the key is moved towards the new server. This happens for almost all the keys, which causes massive data movement every time the cluster size changes. It is like reshuffling a deck of cards when another player is added. Everything has to be dealt again. In short, hash modulo n is easy to implement, but it makes rebalancing very expensive. So it is generally not used in serious systems. Okay, so now let's talk about fixed partition rebalancing. One common strategy is to create many small partitions upfront and assign several to each node. For example, suppose we start a 10 server cluster with 1000 partitions. So each server initially holds 1000 partitions. If a 11 server is added, it doesn't change the partition counts. Instead, the new server steals some partitions from the old server until things balance out again. In other words, we leave the total partitions, for example here 1000 partition as it is and just reassign some of them to the new server. The key and the data inside each partition stays together. Only which server owns each partition changes. Okay, so now let's discuss how it works, when it is useful, pros and cons. So in this, you fix the partition count at the setup, often the large number, and scatter them across all the servers. When nodes change, you migrate each partitions around. For example, one node might give its own 10 partitions to the new node. This is like cutting the pizza into many slices in the advance. When a new guest arrives, you just hand them the pre-cutted pizza slices rather than recutting the pizzas. Okay, so now let's discuss when it is useful. This method is used by systems such as React, Couchbase, Elasticsearch, and Voldemort. It is simple and predictable when the cluster usually grows. It works well if you can estimate the upper bound on future growth, since you set the max partitions initially. Okay, so let's talk about the pros. Because there are many small partitions, adding or removing a server only moves some of its partitions from its old server. It also lets you to account for uneven hardware. Usually the machine can be given more partitions so that it can work more. After rebalancing, no server has too many partitions than other. So that means a fair distribution is restored. Okay, so now let's talk about the cons. You must pick the total number of partitions before running. Too few partitions means each partition is large, so moving them is kind of slow. Too many means each has overhead, indexing, metadata, etc. Also, the initial partition count limits the growth. If you need more servers than partitions, you can't easily add them. In practice, people often set a high number of partitions upfront and don't split or merge later. The key is finding a balance, enough partitions to rebalance smoothly, but not so many that management costs skyrocket. Okay, so now let's talk about dynamic rebalancing. This is another approach which is often used with key range sharding. Here, partitions can split or merge as the data grows or shrinks. Imagine each partition has the upper size limits, for example 10 GB. Once a partition data exceeds that, it automatically splits into roughly equal halves. If a partition becomes a sparse that is too small after deletion, it may merge with its neighbor. This is similar to how the top level of B tree splits and merges the nodes as the data changes. After splitting, one half can stay on the old server and other half move to a different server to spread the load. Okay, so now let's discuss how it works. The system monitors partition sizes. When one is too big, it creates the two new ones in its place and then reassigns it across the nodes. This way, the number of partitions automatically grows with the dataset. For example, HBase will split the region if it crosses 10 GB. After a split, that server can pass that new partition to the new server for rebalancing. Okay, so now let's discuss when it is useful. It is great when the data grows unexpectedly or the data is distributed unevenly. You don't have to guess the partition boundaries in advance. Systems like HBase, RethinkDB, MongoDB use this kind of dynamic rebalancing. Okay, so now let's talk about the pros of using dynamic rebalancing. The cluster adapts to the data size. When the database is small, the partitions are less, so overhead is low. As data grows, more partition appears, preventing any single partition from getting too large. In other words, each partition stays in the size limit by a construction. This keeps the work spread out. You are always splitting the bigger jobs into the smaller ones. Okay, so now let's talk about cons of using it. A fresh database have a single partition or maybe a fewer partition since nothing tells it where to split. That means early on one node does all the work until the first split occurs. This is like having a big cake and only cutting it after it is too large. Until then, everyone else waits. To mitigate this, some system allows the initial pre-split of empty partitions. But that requires guessing the final data distribution. In practice, if you don't pre-split, one node can become a temporary bottleneck until enough splits happen. Okay, so let's move forward. Let's discuss partitioning proportional to nodes, how it works, when it is useful, pros and cons. This is the third strategy where we keep the fixed number of partitions per nodes so that total number of partition grows or shrinks as you add or remove the servers. For example, Cassandra by default uses 256 partitions per node. When you start with the 3 nodes, you have 768 partitions. And with 4 nodes, you have 1024 partitions and so on. This way, each machine handles the same number of partitions. And as the data grows, you add nodes to keep the partition sizes in check. Okay, so let's discuss how it works. Every time you add a node, the cluster increases the partitions so that each node continues to have 256 partitions. Operationally, when a new server joins, it randomly picks the few number of partitions and splits them, taking one half of each splits. The other half of the partition stays with the old owner. Over many partitions, this random choice tends to balance out. Each server gives up a roughly equal share of the data. This method is closely related to the consistent hashing. By selecting the hash ranges at random, it ensures no single split hits all the data. Okay, so now let's talk about when it is useful. This is useful when you can grow the cluster as the data grows. Cassandra and the system using the Katama hashing follows this approach. It keeps each partition size relatively stable, even if the total data volume changes. If data doubles and you double the nodes, each partition ends up the same size as before. Okay, so let's move towards the pros of it. It automatically adapts to the cluster size. Since the partitions per node is fixed, adding a node immediately makes the partitions smaller. This tends to keep the performance steady without huge rebalances of the old data. Also, spreading the splits randomly avoids creating the hot partitions by accident. Let's move towards the cons of it. The randomness can slightly give one node more or less than its fair share in a single rebalance. Though over many partitions, it evens out. Early version of the Cassandra have to tweak the algorithm to avoid some unlucky splits. But in general, having dozens of hundreds of partitions per node makes the process smooth because this method lies on the hash partition. It gives up the range query efficiency, but it makes the data movement very efficient. Okay, so let's discuss automatic versus manual rebalancing. When a database decides when and how to rebalance, it can be automatic, that means the system handles it, or it can be manual, that means the administrator handles it. Okay, so let's talk about the automatic rebalancing first and then manual rebalancing. So in this, some system lets the database to automatically detect imbalances and move out the data without the human input. This is convenient. The cluster manages itself during the normal growth or minor node changes. However, it can be risky. Rebalancing itself is a heavy work, moving lots of data and updating routing. If done at the wrong time, for example at higher peak load or false node failure alert, it can affect the performance or even overload the cluster. For example, suppose one server is slow but it is alive and a system mistakenly thinks it is a dead, and automatic rebalance start moving the partitions somewhere else. This can make the true load worse or even trigger a cascading failure. Okay, so let's discuss about manual rebalancing. Other systems are conservative. They might suggest an optimal new partition layout, but an administrator must approve or trigger it. This human-in-loop makes the rebalancing slower, but much safer. An operator can pick the low traffic time or break the work into stages. In Couchbase, React, Voldemort, for example, the system computes how to rebalance but waits for an admin to apply it. This prevents surprise disruptions. In short, manual mode trades some agility for predictable control. Okay, so in summary, distributed databases needs rebalancing to stay healthy as condition changes. Okay, so let's wrap up. We have discussed rebalancing partitions in distributed database, why simple hashing, that is a modulo and fails, fixed partition rebalancing, dynamic rebalancing, partition proportional to nodes, and the difference between automatic and manual rebalancing. Okay, so if you are still watching this video, then make sure you like the video, comment your doubts, and subscribe to my channel so that it will motivate me to make more such videos. Thank you so much for watching.